Hey, Algebra 2, we're going to go through a quick lesson on graphing logarithmic functions. And then at the end of the lesson, which we'll have to practice during the problem set, we're going to be messing with a few functions and sort of combining functions, but, well, let's just watch. So first of all, graph the points in the table for your assigned function. So if we were in a classroom, we'd be doing this together. But these are the three functions that we are graphing on a coordinate plane for the given domain of 0 to 16. And we're going to sketch curves. I went ahead and did this on Desmos, and we're just going to see the pattern, okay? So here we have log base 10, log base 2, and log base 5, and we're going to see what happens with the graphs. So the red one is log base 10, the blue one is log base 2, and the green one is log base 5. So here we have log base 10, log base 2, and log base 5. I'm trying to show you a pattern, but let's answer some questions about it. Now you're going to have to either split your screen somehow and look at this to the side, maybe take a screenshot of it, because now I need to answer some questions about it, and I have to move on to my screen, but you do not. So the first question we're going to answer is, what does the graph indicate about the domain for your function? And then describe the x-intercepts, and then describe the y-intercepts, and then find the coordinates of the point on the graph where the with a y value of 1. So a y value of 1, a y value of 1, and a y value of 1. So that's what I'm going to do in the next few pages, okay? So first of all, what does the graph indicate about the domain of your function? So what we see here is the domain of all of them is positive real numbers, which we can say okay, so a domain is the x value. Remember the input, the x values, and for this instance of the logarithms, it's all real numbers, which if I want to put it into a notation, I would say from 0 to infinity. So the x values go from 0 to infinity. Describe the x-intercepts of the graph. I circled. They all have an x-intercept at 1. So 1 comma 0, sorry. They all share the same x-intercept. The y-intercept, there is no y-intercept. The y-intercept, the x value is 0, and I can't take the log of 0. It's not a valid log. You can't take the log of 0, just like you can't divide by 0. Okay, so that's why there's no x or no y-intercepts on the graph, or any log graph for that matter. The coordinates of the point on the graph with y value of 1 for log base 10. What color did I do log base 10? Blue. So for log base 10, the coordinate with a y value of 1 is 10 comma 1. For log base 2, well, let's just do 5. We'll do them in order. For log base 5, if you look, the coordinate where the y value is 1 is at 5. I was just making sure. And then for the log base 2, the coordinate where the y value is 1 is at 2 comma 1. There's a cool pattern, right? And now behavior. This is called end behavior. How does the graph act as it's built? I can't spell today. Yes, I know you guys are all laughing like, Miss Carly, you can't spell any day. And what we say for end behavior, we say statements like, as x approaches 0, the function, so the function approaches negative infinity. And if you look at the graph, what are we doing? Let's see. We'll just do a dummy log graph. We can say as x approaches 0, what is your graph doing? Your graph is approaching negative infinity. And the next one, change of color. As x approaches infinity, your graph, your curve, is approaching positive infinity. Okay? So to describe the behavior as x approaches 0, your graph or your end behavior, your function, your curve, is approaching negative infinity. And this is the same for g of x, all of them. Sorry, I'll do that. As x approaches 0, all log graphs would be approaching, well, these 3 log graphs, we're going to get into some different ones that may not, but these 3 log graphs approach negative infinity. And then the end behavior as x approaches infinity. So as x gets bigger and bigger and bigger, your functions, both of your functions also get bigger. Okay? Pretty cool. That end behavior thing, I think this is the first time we've really talked about it. So definitely ask a question if you don't understand. We're going to go through a few more examples. Range, so that's the y values. My y values are going to go from negative infinity to infinity because they will span all of the graph. That's going down, that's going up. It'll never cross over into x equals 0, but the y values are negative to positive. Does this function have any relative maxima or minima? Explain how you know. Well, since the function increases, and there are no peaks, which are the maximas, the relative maximas, or valleys, the minimas, the relative minimas, there are none. So the function increases as you go. There are no peaks, no valleys, therefore no relative maximas or minimas. This was a really awesome summary that I wanted you guys to have your hands on. It's what we did in all of the questions that we just wrote up, but it's in a nice table, and I like nice tables. End behavior as x approaches 0, end behavior as x approaches infinity, y-intercepts, x-intercepts, the points where the y value is 1, etc. So I like that little chart. Okay, let's review this just a tad bit. Random questions. What do these 3 graphs have in common? Some things they have in common. They all cross the x-axis at 1, 0. So their x-intercepts are all at 1, 0. That's something they have in common. There are no y-intercepts. And you can see this in the chart on the last slide. No y-intercepts for any of the graphs. They have the same end behavior. Also, if you look just right here, they all increase super quickly. And then level out. We'll say flatten. Next random question. What do you guys expect log base 3 of x to look like? If you remember, I've got log base 10, which is right there, log base 5, log base 2, And we can tell that because, let's see, 2, 1, 5, 1, 10, 10, 1. I don't know why I got confused in my head. So where would log base 3 go? Well, if I look at 1, 2, 3, 1, it would hit 1 right there, right? So it would follow the same quick rise. It'd go through 1, 0, and then would hit right there. It would be in between, probably a little closer up there, then closer to the 5, or somewhere in between. Yeah, a little closer to the 2. So you've seen the pattern, you see how it works, right? Awesome. All right, we have another one. Graph the points in the table for your sine function. These functions, you can see they're to the base of a fraction, or I had to type into Desmos with a decimal because it didn't like base fractions. So I've got 1/10, 0.5, and 0.2. Cool. So let's see what it looks like. Hey, look, it's upside down, right? Okay, let's label which one is which. This one closest to the x-axis is 1/10. That's a base 1/10. Then we have a base 1/5 and a base 1/2. So as your base gets bigger, it gets further away from the x-axis, right? The last example, as the base got smaller, it got further away from the x-axis. So up here was base 2, and then we had a base 5 and a base 10. Remember? All right, let's see if we can look for our patterns with this one. As you see in Desmos, I had to do the base of a decimal, which is okay. That's all right. Okay, the other things I want to point out. There's my x-intercept, and they're all the same. Y-intercepts are base 10 is, we didn't do, oh, hold on. Let's see what else we can have here. Here, this is at x equals 2, y equals 1, x equals 5, y equals 1, and x equals 10, y equals 1. All right, what is the relationship between your graph in the opening exercise, which was base 10, base 2, and base 5, and your graph from this exercise? It's a reflection. Across the x-axis. Why does this happen? Use the change of base formula to justify what you observed in part A. So let's look at just the log base 1/2 of x. Change of base formula says this is log x over log of 1/2. So I just changed them both to base 10, right? Which is very useful. And I can simplify this more. Log x over log 1 minus log 2. The log of 1 is 0. So this is really what I have. Negative log x over log 2. Which is really negative log base 2 of x. I just reversed the change of base formula, right? So I have log 1/2, log base 1/2 of x is equal to negative log 2, base 2 of x. I don't know why that line was there. So that's why you see that this is a reflection. Because remember, when you put a negative in front of a function, it becomes a reflection over the x-axis. So I've got a negative in front of log base 2 of x, so it's a reflection over the x-axis of the log base 2 one. Pretty cool. All right, let's make sure we understand everything about this particular graph. It's very similar to the last one, just reflects over the x-axis. And I circled a lot of things on the last, when we first introduced the graph. My x-intercept is 1, which we see right here for all 3 graphs. There is no y-intercept for all 3 graphs. The graph passes through the point, this is important, b comma negative 1. Passes through the point b comma negative 1, and let me tell you why. You're going to need this for the problem set. For the first graphs that we threw up there, it passed through log base b of x. For each one, so the first set of graphs, it passed through b comma 1. With this set of graphs, we're passing through b negative 1. So this formula, this graph, pertains to the first set of graphs, and the yellow pertains to this set of graphs. Okay, our base is a fraction, therefore it's passing through b comma negative 1. Our base was a whole number, it passed through b comma 1. Big deal, but it's alright. Our end behavior, okay, as x approaches 0, so as x goes this way, our function increases. As x increases, our function decreases. It's opposite of the previous set of graphs we went through, which makes sense because it's a reflection over the x-axis, right? Alright, this right here is the newest thing that we've introduced on this slide, so we're going to need that for the problem set. Make sure that you write it down. Alright. So, in general, let's try to relate the two things that we've done together. Let's try to figure out what's similar and different about them. So, in general, what is the relationship between the graph of a function y equals f of x and the graph of y equals f of kx? So, alright, for a constant k, we can say that the graph of y equals f of kx is a horizontal shift. When we introduced these shifts to you in the past, I've taught them to my Algebra 1 students, and they're all getting how our translations work, how we stretch and shrink things horizontally, and what our variables, what our k value is when we stretch and shrink things horizontally. Sorry, I can't talk and write at the same time. Horizontal scaling of the graph. I start to forget what I'm doing. Y equals f of x. So we've got the original y equals f of x and the horizontal scaled one, y equals f of kx. And let's figure out how that k affects things, okay? Now we're going to graph some different points where we're going to have a k value in there. So here, my k value is 10, 2, and 5, and how does that affect things? I went ahead and graphed it on Desmos because it's so much easier, and I can take screenshots, and it's great. So here we have log of 10x, log of 2x, and log of 5x. So let's point out some things. Okay, where the graphs intersect is no longer at ordered pair 1, 0. Remember, they always had an x-intercept at 1, 0, and that's where all the graphs intersected also. So that went up by a unit of 1. Let's see what else we can see. The graph of log base 10 of 10x should go 10, 1, right? Well, it's now up at 10, 2. The green one should be at 5, 1. It's now up at 5, 2. And the blue one should be at 2, 1. It's now up at 2, 2. It looks like everything was a vertical translation by a +1. So from opening exercise where we graphed y equals log x, log base 2 of x, and log base 5 of x. That was our opening exercise, remember? Now we did a vertical translation up 1. Describe the transformation. I just did. The graph is the opening exercise, but a vertical translation by a unit of 1 up. So I just said it, but let's do it again. Vertical translation up 1 unit. Do your answers to exercise 2, part A agree? If not, use the properties of logarithms to justify your observations in part A. No, they actually don't. If you look back to exercise 2, they don't appear to agree, but let's do our properties of logarithms. So log base b of bx equals log base b of b plus log base b of x. And when these are the same, I've got 1. So they actually do. If I look at log base 10 of 10x, that's log base 10 of 10 plus log base 10 of x. 1 plus log base 10 of x. So it does work. If we compare those, they are similar. Okay, that's our lesson summary. I'm going to go ahead and do an example from your problem set that didn't get covered in the classwork all that well. I'm going to problem set 9, and I'm going to do 2 problems for you. Sorry, not problem set 9. Lesson 17 in the problem set number 9. Okay, these are a lot of fun, but they didn't cover how to do them in the lesson, so let's do another slide. All right, let's do number 9A first. So I have if f of x equals x squared plus x, find h of x equals f of x plus 1. This just means I need to substitute x plus 1 wherever I see an x. Okay? So h of x equals x plus 1 squared plus x plus 1. Substitution. I can go ahead and simplify, FOIL that first thing. I have x squared plus 2x plus 1 plus x plus 1. Now simplify. X squared plus 3x plus 2. That's h of x. I lied. We're going to do c also. So if f of x equals log of x, find h of x equals f of the cubed root 10x when x is greater than 0. So go ahead and substitute. So wherever I see an x, I need to write that in. Sort of crazy, I know. So I have log of cubed root 10x. And I should say that is equal to h of x, sorry. So let's go ahead and simplify. I'm going to take that 1/3 out to the front. Log of 10x. 1/3 log 10 plus log x. Log 10 is 1. 1 plus log x, and then distribute that 1/3 if you'd like to. I can do this. Either answer would be acceptable in my book. You can distribute or you cannot. Cool? Alright, let's try. No, I think you can do number 10. Alright, I think I gave you enough. Well, no, let's do one more. Don't you love how I argue with myself in front of you guys? We're going to do 10 part A has been done for you. Alright, let's try part B. this one says for each one I'm doing, for each I, and I, I'm doing a different type of problem. So I need to find f of g of x. For double I need to find g of f of x. And then for triple I need to find f of x. So it's not difficult as long as you know what you're looking at. So for part 10, we're going to do b. F of x equals 1/4 x minus 8, and g of x equals 4x plus 1. So for part I need to find, f of g of x. So that means I'm going to plug g of x in wherever I see an x. I know it's crazy, but it works. So 1/4 4x plus 1 minus 8, and then simplify. So I'm going to distribute that 1/4, x plus 1/4 minus 8 equals x plus 7 3/4. Okay, double I need to do g of f of x. So wherever I see an x, I'm going to put f of x. So right there, I'm going to substitute. So g of x of f of x. Distribute that 4. I've got x minus 32 plus 1, x minus 31. And then triple I, f of f of x. So I'm substituting f of x in for the x's, which is silly. You're just practicing some funny math. Distribute that 1/4. I have x minus 2, minus 8, x minus 10. All right, those are your examples. We're done. Good job.